These are the boundaries of everything you will ever be able to see, and beyond them, physics says something is almost certainly still there. 93 billion light-years wide. That's the observable universe, and it is not the same thing as the universe itself. Before you do anything else today, hit like on this video and subscribe, because what you're about to hear will change the way you look at the night sky. Start with the number, because the number is where all of this gets strange. The observable universe measures roughly 93 billion light-years across, edge to edge, with Earth sitting more or less in the middle of that sphere. And here's the part that trips people up. The universe itself is only 13.8 billion years old. If light has only had 13.8 billion years to travel, how can the sphere we can see be almost 7 times wider than that number would suggest? The answer is that space itself has been stretching the entire time that light has been traveling toward us. When a photon left some ancient galaxy billions of years ago, that galaxy was much closer to where Earth would eventually form. But space expanded underneath that photon for its entire journey, and by the time the light finally reaches our telescopes, the galaxy that sent it has been carried much farther away by the expansion. Astronomers call the distance to that boundary the particle horizon, and it sits at about 46.5 billion light-years away from us in every direction, which is where the 93 billion light-year diameter comes from. It's not a measurement of how far light has traveled. It's a measurement of where the source of that light actually is right now, accounting for 13.8 billion years of cosmic stretching. At the very edge of what we can detect sits the cosmic microwave background, the oldest light in existence, radiation that was emitted when the universe was only 380,000 years old. Before that point, the universe was so hot and dense that light couldn't travel freely at all. It was trapped, scattering constantly off free electrons, the way light struggles to travel through thick fog. Then, at 380,000 years old, the universe cooled enough for atoms to form, electrons settled into orbits around nuclei, and space became transparent for the first time. That's the wall we're up against. We can see almost all the way back to the beginning, but not quite, because before that moment, there was no clear light to see. And here's something that should unsettle you a little. The observable universe is not fixed. It's shrinking, functionally, even while it appears to grow. Every single second, roughly 20,000 stars cross a threshold and become permanently unobservable from Earth, pushed beyond our reach by the relentless expansion of space, which is accelerating. Billions of years from now, astronomers on Earth, if there still are any, will look up and see nothing beyond our own local group, a cluster of a few dozen galaxies. Everything else will have receded past the point where its light can ever catch up to us again. The universe isn't just too big to see all of. It's actively hiding more of itself from us with every passing moment. It helps to put a number on just how much is packed inside the boundary we've been describing this whole time, if only to make the scale of everything beyond it a little more tangible. For roughly 2 decades, the working estimate for how many galaxies exist within the observable universe, based largely on the original Hubble Deep Field images captured in the mid-1990s, sat at around 100 to 200 billion. In 2016, a team led by Christopher Consolis at the University of Nottingham revised that number dramatically upward, using improved deep field imaging from the Hubble Space Telescope combined with 3-dimensional modeling of galaxy density at different distances and different points in cosmic history. Their conclusion, published in the Astrophysical Journal, put the true figure at a minimum of 2 trillion galaxies, roughly 10 times higher than the old estimate. The revision came from accounting for enormous numbers of small, faint galaxies, similar in size to the dwarf satellite galaxies orbiting the Milky Way, which existing telescopes simply hadn't been sensitive enough to detect directly. Consolis noted, at the time, that current technology only allowed astronomers to actually observe roughly 10% of those 2 trillion galaxies, meaning the overwhelming majority of everything inside the observable universe, over 90% of it, remains too faint to study with any telescope operating today. That 2 trillion figure describes only what's packed inside the 93 billion light-year sphere we can, in principle, ever hope to see. It says nothing at all about the volume of space beyond it, the same space this entire video has been circling around, which every serious cosmological model treats as continuing on, unbroken, indefinitely. The most recent challenge to the standard picture of the early universe didn't come from theorists at all. It came directly from images. The James Webb Space Telescope, launched in December of 2021 and considerably more sensitive to the faint infrared light of extremely distant galaxies than its predecessor, the Hubble Space Telescope, began returning its first deep-field images in the summer of 2022. Almost immediately, astronomers ran into a problem nobody had fully anticipated. JWST kept finding galaxies at extraordinarily high redshift, meaning extraordinarily far away and extraordinarily early in cosmic history. Some observed as they existed when the universe was only 300 to 500 million years old, that were simply too big, too bright, and too massive to exist yet, according to standard models of how galaxies form and grow within the accepted cosmological framework. One particularly striking example, a galaxy designated GNZ11, was spectroscopically confirmed to be sitting at a point just 430 million years after the Big Bang, and astronomers studying it described it bluntly as a remarkable galaxy with extreme properties for its age. The core of the problem is straightforward. In the standard model of galaxy formation, galaxies grow gradually, starting as small, irregular collections of gas and young stars that slowly merge and mature over billions of years into the larger, more structured spiral and disk galaxies we see nearby, including our own Milky Way. The standard model places a hard upper limit on how much stellar mass a galaxy of a given age should be able to accumulate, based on how much ordinary matter the surrounding dark matter structure could plausibly have funneled into it by that point in cosmic history. Several of the galaxies JWST turned up sat right at, or in some analyses beyond, that theoretical ceiling, assembling what looked like a mature galaxy's worth of stars in a fraction of the time the standard model says should be required. Astrophysicists studying the problem, including Mike Boylan-Colchin at the University of Texas, described the earliest reported cases as posing a serious, direct challenge to the prevailing cosmological model if the measurements held up under closer scrutiny. The debate over what to make of it has stayed genuinely unresolved and remarkably active. Some of the galaxies initially flagged as impossibly massive have since had their distances and masses revised downward once follow-up spectroscopy, a more precise way of confirming a galaxy's exact redshift than the original brightness-based estimates, became available, easing the tension in those specific cases. Other studies, drawing on larger, more carefully vetted samples of spectroscopically confirmed galaxies, have found no significant conflict with the standard model at all, suggesting some of the earliest, most dramatic headlines may have jumped ahead of the data. But a meaningful subset of genuinely puzzling confirmed cases has persisted, and researchers have proposed a range of possible explanations, everything from unexpectedly efficient star formation in the earliest galaxies to the surprising discovery that many of these galaxies possess more organized, disk-like structures than anyone expected them to have this early, to more exotic ideas involving cosmic strings or other physics beyond the standard model entirely. As of the most recent published research, no single explanation has been confirmed, and the question of exactly how the universe managed to build such large, seemingly mature galaxies so quickly after the Big Bang remains one of the most active, unresolved puzzles in observational cosmology. A reminder that even the parts of this story we thought were settled keep turning up new, genuinely open questions every time a more capable telescope gets pointed at the sky. So how do we even know any of this? The story of how humanity found the edge of what it can see starts, almost comically, with a wall of static that two radio astronomers couldn't get rid of. In 1964, Arno Penzias and Robert Wilson, working at Bell Labs in Holmdel, New Jersey, were using a large horn-shaped antenna, originally built for satellite communication, to study radio emissions from our own galaxy. No matter what they did, they kept picking up a faint, steady hum of noise, coming from every direction in the sky at once, day and night, in every season. They checked the wiring. They checked the amplifiers. At one point, they even climbed inside the antenna and cleared out a colony of pigeons that had nested there, thinking the mess might be the source of the interference. It wasn't. The noise stayed exactly the same, no matter what they removed. What Penzias and Wilson didn't know, at least not yet, was that just 30 miles away, a team at Princeton University, led by physicist Robert Dick, working alongside Jim Peebles, was actively trying to build a detector to search for exactly this kind of signal, a faint afterglow of radiation left over from the Big Bang, predicted years earlier but never confirmed. When Penzias eventually called Dicke to ask if he had any idea what could be causing this persistent, direction-independent noise, the two teams quickly realized what had happened. They published their results together in 1965 in back-to-back papers in the Astrophysical Journal, one describing the detection, the other explaining what it meant. The universe itself had a temperature, a faint microwave glow left over from its own birth, sitting at just a few degrees above absolute zero. For that discovery, Penzias and Wilson were awarded the Nobel Prize in Physics in 1978. That discovery alone confirmed the Big Bang happened. It didn't yet tell scientists much about the fine detail of that afterglow, the subtle variations that would eventually explain how a smooth, uniform early universe grew into one filled with galaxies, stars, and eventually us. That took another generation of technology, launched into space. NASA's Cosmic Background Explorer, known as COBE, lifted off on November 18, 1989, becoming the first satellite built specifically to study the cosmic microwave background across the entire sky. In April of 1992, COBE's science team announced they'd found what they were looking for: incredibly faint temperature ripples, differing by only about 1 part in 100,000 across the sky, wrinkles in the fabric of the early universe. The announcement made front-page news around the world. Those wrinkles were the seeds. Regions that were ever so slightly denser than their surroundings would go on, over billions of years, to collapse under their own gravity and become the galaxies we see today. Without those tiny variations, gravity would have had nothing to grab onto, and the universe would have stayed a smooth, structureless soup forever. COBE's principal investigators, John Mather and George Smoot, were awarded the Nobel Prize in Physics in 2006 for the discovery. COBE was a good start, but it was a blunt instrument compared to what came next. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, WMAP, specifically to map those temperature fluctuations in far greater detail. WMAP spent its first 6 months in orbit building a complete map of the entire sky, then scanned the sky repeatedly over the following 9 years, sharpening the picture with each pass. Compared to COBE, WMAP improved the resolution of the temperature map by a factor of roughly 70,000. That leap in precision let cosmologists, for the first time, actually calculate hard numbers for things that had previously only been theoretical: the age of the universe, its overall geometry, how much of it was made of ordinary matter versus dark energy. Then, starting in 2009, the European Space Agency's Planck satellite pushed the resolution even further, covering a wider range of frequencies at even higher sensitivity, giving cosmologists their most detailed and most trusted picture yet of the light left over from the birth of the universe. Averaged across the whole sky, Planck confirmed that the cosmic microwave background matches what's called a black body spectrum, the signature of pure thermal radiation, at a temperature of just 2.73 degrees above absolute zero, with those same telltale ripples layered on top, now mapped with extraordinary precision. 3 missions, 3 generations of instruments, each one confirming and sharpening the picture the last one had found. It's rare, in science, for a chain of confirmation to be this clean. None of the numbers in this video, the 93 billion light-year diameter, the 2 trillion galaxies, the distance to the Great Attractor, actually mean anything without a reliable way to measure distance across the universe in the first place. And that entire foundation traces back to a woman who spent years quietly comparing photographic plates by hand at the Harvard College Observatory. Henrietta Swan Leavitt was employed there starting in the early 1900s in a position formerly titled Curator of Astronomical Photographs, one of a group of women hired by observatory director Edward Pickering to catalogue the brightness of stars from glass photographic plates, work that was, at the time, considered too tedious and administrative to be handed to male astronomers. Leavitt's specific assignment was to identify variable stars, ones whose brightness rises and falls over time, within the Small Magellanic Cloud, a small satellite galaxy near the Milky Way. Using an instrument called a blink comparator, which rapidly alternated between 2 photographs of the same patch of sky taken weeks apart, Any star that had changed brightness would appear to flash. Working this way, Leavitt catalogued 1,777 variable stars, publishing her first results in 1908 and a more detailed follow-up study in 1912. Buried inside that painstaking cataloguing work, Leavitt noticed something that would end up reshaping the whole field of astronomy. For one particular class of these stars, called Cepheid variables, the brighter ones consistently took longer to complete a full cycle of brightening and dimming. Because Leavitt could reasonably assume that every Cepheid within the Small Magellanic Cloud sat at roughly the same distance from Earth, any difference in how bright they appeared had to reflect a genuine difference in how bright they actually were, not just how far away they happened to be. That let her establish a clean mathematical relationship between a Cepheid's pulsation period and its true, intrinsic brightness, a relationship astronomers now call the Leavitt law. The practical consequence was enormous. Find a Cepheid variable star anywhere in the sky, time how long it takes to complete one pulsation cycle, and Leavitt's relationship tells you exactly how bright that star actually is. Compare that true brightness to how dim it appears from Earth, and basic physics, the same inverse square law that makes a flashlight look dimmer the farther away it is, tells you precisely how far away the star sits. Astronomers call this kind of object a standard candle, a light source whose true brightness is already known, making it usable as a reliable distance marker. It's difficult to overstate how much of modern cosmology rests on Leavitt's original insight. It was Leavitt's period luminosity relation, calibrated by other astronomers in the years that followed, that Edwin Hubble used in the 1920s to measure the distance to the Andromeda Nebula, proving for the first time that it was an entirely separate galaxy lying far outside the Milky Way. And it's the very same relationship, refined with a century of better instruments, that the SH0ES collaboration uses today as the foundation of the modern cosmic distance ladder. The exact measurement chain sitting at the center of the Hubble tension discussed earlier in this video. Leavitt herself never received much recognition during her own lifetime for the discovery, and she died in 1921 at the age of 53 from cancer, years before Hubble's own famous 1929 announcement of the expanding universe, a discovery her own careful, painstaking measurements of blinking photographic plates had quietly made possible. It's worth being precise about exactly what astronomers mean when they talk about a distant galaxy's redshift, since that single measurement quietly underlies almost every distance and every age mentioned throughout this entire video. When a source of light moves away from an observer, its light waves get stretched out, shifted toward the longer, redder end of the visible spectrum, the same basic Doppler effect responsible for a passing car's engine sounding lower-pitched as it drives away. Astronomers measure this shift by comparing the exact wavelengths of light a distant galaxy emits, wavelengths tied to the specific, unchanging physics of hydrogen, helium, and other elements, against how those same wavelengths appear stretched out by the time the light reaches our telescopes. The larger the shift, the faster the object appears to be receding, and, thanks to Hubble's law, the farther away it generally sits. There's a subtlety here that trips up even fairly careful thinkers though, and it's directly relevant to everything this video has covered about the expanding universe. For nearby objects, that redshift really is mostly an ordinary Doppler effect, caused by galaxies physically moving through space, the same way the Great Attractor is genuinely tugging our own galaxy toward it. But for extremely distant galaxies, especially the kind of high redshift galaxies Geodioist has been finding from the universe's first few 100 million years, the dominant cause of the redshift isn't motion through space at all, it's the stretching of space itself. As a photon of light travels for billions of years across an expanding universe, the space it's traveling through keeps stretching underneath it, stretching the photon's own wavelength right along with it. Exactly the same mechanism responsible for the particle horizon sitting so much farther away than the universe's actual age would otherwise suggest. Astronomers call this specific version cosmological redshift, and it's mathematically distinct from ordinary Doppler shift, even though both produce the same basic observed effect of light shifting toward the red end of the spectrum. It's this distinction, cosmological redshift caused by the expansion of space rather than objects flying through a fixed, unmoving backdrop, that makes concepts like the particle horizon and the cosmological event horizon possible in the first place. and it's the same basic measurement, refined from Vesto Slipher's earliest observations in the 1910s through Hubble's 1929 breakthrough to the millions of precise redshifts DESI is cataloging today, that every single distance estimate in this video ultimately traces back to. Leavitt's period luminosity relation only works, though, once you already have at least one reliable ruler to calibrate it against. And that very first rung of the entire cosmic distance ladder relies on a method far older than photography or spectroscopy, one the ancient Greeks understood the geometry of, even if they lacked the instruments to actually use it. It's called parallax, and it works on exactly the same principle that makes a nearby lamppost appear to shift position against a distant skyline when you look at it first with your left eye closed, then your right. Astronomers apply the same trick on a cosmic scale, photographing a relatively nearby star once, then photographing the same patch of sky again 6 months later, once Earth has traveled to the opposite side of its orbit around the Sun. Against that 186 million-mile baseline, a nearby star will appear to shift very slightly against the much more distant background stars behind it. And simple trigonometry, the same geometry taught in any high school classroom, converts that tiny angular shift directly into a precise distance, with no assumptions about brightness or luminosity required at all. Parallax is the only fully direct, geometric way to measure distance to another star, and for most of the history of astronomy, it was also the most limited, reliably usable only for the nearest few hundred light-years, since the parallax shift for anything farther away becomes too small to measure accurately with ground-based telescopes. That changed dramatically with the European Space Agency's Gaia satellite, launched in 2013 specifically to measure the parallax, and therefore the precise distance, of well over 1 billion stars across the Milky Way with extraordinary accuracy. It's this small, elegant, geometry-based method that ultimately calibrates everything built on top of it. Parallax measurements pin down the true distance to nearby stars, nearby Cepheid variables among them, which lets astronomers calibrate Leavitt's period luminosity relation with real, independently verified numbers rather than assumptions, which then lets Cepheids in more distant galaxies calibrate exploding type Ia supernovae as an even brighter, even more distant standard candle, which finally lets those supernovae calibrate the expansion rate of the universe itself. It's a genuine ladder, each rung resting entirely on the one below it, and the whole towering structure, ultimately responsible for every distance mentioned in this video, traces all the way back down to the simple geometric fact that your two eyes see slightly different views of a nearby object, scaled up to the width of Earth's entire orbit around the Sun. That transparency didn't come with an obvious story attached, at first. Cosmologists needed one more thread of evidence before the picture we've just walked through could snap into focus, and that thread came not from the light itself, but from figuring out that the universe was expanding to begin with. It started with a Belgian Catholic priest and physicist named Georges Lemaitre, who in 1927, working from Einstein's own equations of general relativity, worked out that the universe couldn't be standing still. He proposed instead that space itself was expanding, and that the light from distant galaxies should be stretched, shifted toward the red end of the spectrum, in proportion to their distance from us. Lemaitre published the result in French, in a relatively obscure Belgian journal, and almost nobody noticed. When he personally handed Einstein a copy of the paper at the Solvay conference that same year, Einstein, according to Lemaitre's own later recollection, told him his mathematics was correct, but his physics was abominable, because Einstein, at the time, still believed the universe was static and unchanging, a belief so strong that years earlier, in 1917, he had inserted an extra term into his own equations, a cosmological constant, specifically to force his model of the universe to stop expanding or contracting and just sit still. 2 years later, in 1929, the American astronomer Edwin Hubble, working with far more extensive observational data than Lemaitre had access to, published his own paper demonstrating a clear, linear relationship between how far away a galaxy is and how fast it appears to be moving away from us. Unbeknownst to Hubble at the time, he had independently confirmed exactly what Lemaitre had already calculated 2 years earlier from pure theory. Hubble's data was better, his platform was larger, and history, somewhat unfairly to Lemaitre, ended up naming the relationship Hubble's law. Confronted with Hubble's results, Einstein reportedly abandoned his static universe model, and in his own later reflections, according to the physicist George Gamow, described the cosmological constant he'd added purely to keep the universe standing still as the biggest blunder of his life, though some historians have since raised doubts about whether Einstein used those exact words. What makes that walk back genuinely ironic is that decades later, in 1998, when astronomers discovered dark energy accelerating the universe's expansion, they found themselves reaching for a mathematical term that looks almost identical to the one Einstein had angrily discarded, meaning the constant he called his biggest mistake may have actually been an early, accidental description of one of the most important discoveries in modern cosmology. In 1931, Lemaitre pushed his own idea further, proposing that if the universe was expanding now, running the expansion backward in time meant it must have originated from a single, extremely dense, extremely hot point, which he called, in his own memorable phrase, the primeval atom. That idea, refined over the following decades by physicists including George Gamow, became the foundation of what we now call the Big Bang model. But it had a serious, well-organized rival for over a decade. In 1948, astronomer Fred Hoyle, working with Hermann Bondi and Thomas Gold, proposed an alternative called the steady-state theory, arguing that the universe had no beginning and no end at all, that it looked essentially the same at any point in time, with new matter continuously and very gradually created to fill the gaps left behind as existing galaxies drifted apart from each other. It was Hoyle himself, in a BBC radio broadcast on March 28, 1949, who first used the term Big Bang on air, describing the rival theory as the idea that all matter in the universe was created in one Big Bang at a particular time in the remote past. Popular accounts have long claimed Hoyle meant the phrase mockingly, as a put-down of a theory he rejected, though some historians who've reviewed the original broadcast transcript argue that reading may be overstated and that Hoyle used the term more descriptively than derisively. Either way, the name didn't even catch on right away. It took roughly 2 decades, until sometime in the 1970s, for Big Bang to become the standard term, well after the steady-state theory it was coined to contrast against had already lost the argument, thanks in large part to the discovery Penzias and Wilson stumbled onto in 1965. A steady-state universe with no hot early phase had no reason to produce a uniform, leftover microwave glow filling the entire sky. The Big Bang model did, and predicted it in advance. That single piece of evidence effectively ended the steady-state theory's standing as a serious competitor. The cosmic microwave background isn't the only piece of leftover evidence from the universe's earliest moments still lying around for anyone to check. There's a second, completely independent line of proof, tucked into the actual chemical makeup of the universe, and it comes with one of the better inside jokes in the history of physics. In the years leading up to the 1965 discovery of the microwave background, physicist George Gamow, working with his graduate student Ralph Alpha, developed the theory that the intense heat and density of the very early universe should have fused hydrogen into helium and a handful of other light elements within the first few minutes after the Big Bang, a process now called Big Bang nucleosynthesis. Their calculations, published in 1948, predicted that roughly 1/4 of all the ordinary matter in the universe, by mass, should be helium, produced in that brief nuclear furnace before everything cooled and expanded too much for fusion to continue. When the paper went to print, in the April 1, 1948 issue of the journal Physical Review, Gamow couldn't resist a joke. His friend and colleague Hans Bethe hadn't actually contributed to the research at all, but Gamow added his name to the author list anyway, purely so the finished paper would be credited to Alpha, Beta, and Gamow, a pun on the first 3 letters of the Greek alphabet. The nicknames stuck, and the Alpha Beta Gamma paper, as it's still called today, became one of the foundational documents of modern cosmology, predicting a specific, checkable number years before anyone had the tools to measure it precisely. Decades of subsequent observation have confirmed that prediction with remarkable precision. Astronomers measuring the chemical composition of the oldest, most pristine gas clouds they can find, regions of space barely touched by the element-generating fusion, inside later generations of stars, consistently find helium making up close to the predicted 1/4 of ordinary matter by mass, along with trace, similarly predicted amounts of deuterium and lithium. It's a completely separate, independent confirmation of the hot Big Bang model, arrived at through entirely different physics and entirely different instruments than the cosmic microwave background discovery. And the two lines of evidence agree with each other closely enough that between them, they leave very little room for doubt about what happened in the earliest minutes of the universe's existence, whatever remains uncertain about what came before it, or what lies beyond the boundary of everything we can currently see. So what fills the space beyond that boundary? This is where the honest answer has to start, with a distinction most people never learn. There is a difference between the edge of what we can observe and the edge of what exists. Nothing in physics suggests that the particle horizon is a wall, or an edge, or a place where the universe simply stops. It's an horizon in the truest sense, the same way the horizon on the ocean isn't the edge of the sea. Sail past it, and there's more ocean waiting. Cosmologists overwhelmingly expect that the universe continues well beyond what we can see, and possibly forever. Before you can understand why cosmologists expect more universe beyond what we see, you have to understand what was broken about the old picture, the plain Big Bang model with no inflation attached. That older model had 3 specific problems, and each one, on its own, was serious enough to make physicists suspicious that something was missing. The first is called the horizon problem. The cosmic microwave background, that same afterglow Penzias and Wilson stumbled onto, is remarkably uniform, with a temperature that differs by only about 1 part in 100,000 across the entire sky. That sounds like a small detail, but it's actually deeply strange. Under standard expansion, without inflation, opposite sides of the observable sky would have been too far apart, at the time that light was emitted, to have ever been in contact with each other. They would never have had the chance to exchange heat, or energy, or any kind of information, and yet they arrived at nearly identical temperatures anyway, to extraordinary precision. It's a bit like walking into 2 separate rooms, on opposite sides of a building, that have never been connected by so much as a shared vent, and finding both rooms sitting at exactly the same temperature, down to a fraction of a degree, with no plausible way that could have happened by chance. The second is the flatness problem, sometimes called the oldness problem, and it's a fine-tuning issue. The overall geometry of the universe depends on how its total density compares to a specific critical value. If the early density had been even slightly higher or lower than that critical value, the difference would have snowballed dramatically over billions of years, curving the universe into something wildly different from what we see today. For the universe to look as flat as it does now, 13.8 billion years later, the density at the very beginning would have needed to be tuned to an extraordinary degree of precision. Physicist Robert Dicke first raised this puzzle formally in 1969, and it sat there, unresolved, for over a decade. The third is the magnetic monopole problem, and it actually came first, historically, as the very problem Alan Guth was originally trying to solve. Grand unified theories, the leading attempts in the 1970s to merge the fundamental forces of physics into a single framework, predicted that the extreme heat of the very early universe should have produced enormous numbers of magnetic monopoles, hypothetical particles carrying a single, isolated magnetic pole rather than the paired north and south poles every ordinary magnet has. Despite decades of searching, not a single one has ever been detected. Guth wasn't sitting around in 1979 trying to explain the smoothness of the cosmic microwave background or the flatness of space. He was a particle physicist trying to figure out why the universe wasn't drowning in monopoles that the leading theories of the time said it should be full of. What he found, almost by accident, was that a particular kind of false vacuum state, if it existed in the very early universe, would generate an exponential expansion of space according to the equations of general relativity. And that same exponential expansion, it turned out, would also dilute any early population of monopoles down to essentially undetectable levels, simply by spreading them out over an incomprehensibly larger volume of space. In solving the problem he'd actually set out to solve, Guth stumbled into a mechanism that also solved the flatness problem and the horizon problem almost as a side effect. Inflation smooths out the geometry of space the same way blowing up a wrinkled balloon to an enormous size makes its surface look locally flat, even though the balloon started out crumpled and uneven. And it solves the horizon problem by proposing that the entire region that would eventually become our observable universe started out as an impossibly tiny patch, small enough that every part of it really was in close contact with every other part, sharing heat and settling into the same temperature, before inflation then stretched that tiny, uniform patch out to cosmic size. That expectation that there's more universe out there than what inflation smoothed into our observable patch comes from a theory that reshaped cosmology in the early 1980s, called inflation. In 1980, Alan Guth, working at MIT, proposed that in the first unimaginably brief fraction of a second after the Big Bang, the universe underwent an episode of exponential expansion, ballooning outward at a rate far faster than the speed of light would ordinarily allow, because it was space itself doing the stretching, not anything moving through space. Guth wasn't trying to describe how big the universe would eventually become. He was trying to solve those nagging problems with the traditional Big Bang model, and inflation solved them all, elegantly, by proposing that a tiny patch of space stretched so violently and so fast that whatever unevenness existed beforehand got smoothed out almost completely. But Guth's original version of the theory had a serious flaw, one that took a couple of years and several physicists working independently to fix. If inflation happened the way Guth first described it, there was no clean way to end it. The process would create expanding bubbles of ordinary space inside a background that kept inflating, but those bubbles couldn't grow fast enough to link up and produce the smooth, uniform, hot universe that we actually observe. Physicists called this the graceful exit problem, and in 1982, it was resolved independently by André Linde, then working in Moscow, and separately by Andreas Albrecht and Paul Steinhardt. Their fix, known as new inflation, replaced the messy bubble collisions with something more like a slow, continuous roll from one state of the universe to another, avoiding the pile-up entirely. Alan Guth's own account of the night he discovered inflation is worth telling in full, because it's one of the more well-documented eureka moments in the history of physics, and it captures just how unglamorous a genuine scientific breakthrough can look from the inside. In December of 1979, Guth was 32 years old, unemployed in any permanent sense, drifting between short-term postdoctoral positions with a wife and a new baby at home, working out of a rented house near the Stanford Linear Accelerator Center. He wasn't trying to reinvent cosmology. He was working late at night on the specific, narrow problem of magnetic monopoles, trying to understand why grand unified theories predicted the early universe should have produced huge numbers of them when observations showed none. On the night of December 6th, sitting at his desk, he worked through the consequences of a particular kind of false vacuum state and realized it would drive the early universe into a period of runaway exponential expansion. The following morning, Guth biked to his office in a reported 9 minutes and 32 seconds, sat down, carefully worked through the calculations in his notebook, and at the top of a fresh page wrote, in all capital letters and boxed in twice for emphasis, the words, "Spectacular realization." He shared the news that same day with a colleague at the lab, the physicist Leonard Susskind, who would later become one of the key figures behind the holographic principle and the string landscape. Suskind's reported response, on hearing that his friend had potentially just solved several of the biggest open problems in cosmology, was simply, the most amazing thing is that they pay us for this. Guth's original notebook, spectacular realization and all, is now on permanent display at the Adler Planetarium in Chicago, sitting alongside historical artifacts from Galileo and Copernicus, a fitting home for the handwritten origin of the idea that, more than any other, shaped how modern cosmologists think about everything discussed in this video. And that's when things got genuinely strange, because in solving that problem, Linda noticed something nobody had fully appreciated. Inflation, once it starts, doesn't have to stop everywhere at once. In fact, in most of the mathematical models that describe it, inflation doesn't stop everywhere at once. It ends in some regions, producing pockets that cool down and become universes like our own, while in other regions, the inflationary expansion just keeps going, forever, spawning new pockets endlessly. Linde called this eternal inflation, and by 1983, Paul Steinhardt, working with Alexander Vilenkin, had confirmed the same unsettling conclusion from a different angle. Once inflation begins, it appears to become self-reproducing, generating what physicists now call pocket universes or bubble universes, without any obvious end. Alan Guth himself, describing the picture decades later, put it about as plainly as a physicist ever does. Once inflation starts, he said, it never stops completely. In a given region it might end, and space and time settle into something that looks like the smooth, expanding universe we live in. But everywhere else, the surrounding space keeps expanding exponentially, bubbling forever, throwing off new pockets the way a pot of boiling water throws off bubbles that never stop forming. Guth went further in a 2007 paper on eternal inflation, writing that inflationary cosmology suggests that even though the observed universe is incredibly large, it's only an infinitesimal fraction of the entire universe, not a metaphor, an actual claim, grounded in the mathematics of the theory that best explains what we do observe. Inflation's scientific track record includes at least one very public, very instructive failure, and it's worth telling honestly because it shows exactly how the field is supposed to work when a claim outruns the evidence behind it. In March of 2014, a team of researchers operating a telescope called BICEP-2, based at the South Pole, called a press conference at the Harvard-Smithsonian Center for Astrophysics to announce what they described as the first direct evidence of gravitational waves generated during cosmic inflation. Inflation, if it happened the way theorists predicted, should have generated ripples in space-time itself, primordial gravitational waves, which in turn would have left a very specific, faint twisting pattern in the polarization of the cosmic microwave background, a signature physicists call a B-mode. The BICEP-2 team reported detecting exactly that pattern and reported it at a strength notably higher than most theorists had expected, describing the find, according to one of the project's co-leaders, as looking for a needle in a haystack and instead finding a crowbar. The announcement made headlines around the world, with some commentators speculating openly about a future Nobel Prize. The celebration didn't last the year. Skeptics immediately raised a specific concern. Polarized dust drifting throughout our own Milky Way galaxy can produce a nearly identical twisting pattern in the sky, and the BICEP-2 team's estimate of how much of that galactic dust was contaminating their small patch of observed sky had relied on models and public estimates, rather than on direct, independent dust measurements, because the most relevant data from the European Space Agency's Planck satellite hadn't been fully released yet. When Planck's dedicated dust polarization maps did become available later that year, they showed there was considerably more galactic dust in the observed region than the BICEP-2 team had assumed. A joint analysis combining the BICEP-2, Keck array, and Planck data, published in early 2015, found that once the dust contribution was properly subtracted out, almost no statistically significant signal remained, nowhere near enough to support a confident detection of primordial gravitational waves. Princeton cosmologist David Spergel, who had raised early doubts about the original result, summarized the walkback bluntly. The team had effectively withdrawn their claim of detection. It didn't mean inflation itself was wrong. Every other piece of supporting evidence, the flatness of space, the statistical pattern of ordinary temperature fluctuations, the horizon problem inflation was built to solve, remained intact. It meant one specific, exciting, headline-generating piece of evidence for inflation had been an illusion, created by underestimated dust in our own galactic backyard. The search for a genuine detection of those primordial gravitational waves, using instruments specifically built to separate the cosmic signal from the galactic dust this time, has continued ever since, and as of the most recent published constraints, still hasn't found one. Andre Linde, who moved to Stanford University and became one of the most cited cosmologists alive, spent decades developing the implications of what he'd found. In 2017, he published a paper called A Brief History of the Multiverse, tracing everything the field had learned since his original 1982 insight. One of the most cited images from his work is deceptively simple, a diagram showing a field of separate blobs, each one a pocket universe, born at different times during an ongoing, eternal process of inflation, some connected to their parent universe by a kind of bridge that may or may not still exist, others fully disconnected. And crucially, different pocket universes, in this picture, don't have to share the same physics. The constants of nature that we take for granted, the strength of gravity, the mass of an electron, could vary from one pocket to the next, set randomly as each new region breaks off and settles into its own stable state. If that sounds like it's edging into multiverse territory, that's because it is, and the person who did more than almost anyone to organize that territory into something researchers could actually argue about is a physicist named Max Tegmark at MIT. Starting with a widely read 2003 article in Scientific American, and later expanded in his book Our Mathematical Universe, Tegmark proposed sorting multiverse concepts into 4 distinct levels, ranked roughly by how speculative and how different from our own universe they get. Level 1 is the least controversial, and honestly, it's less a bold new claim than a direct consequence of 2 things most cosmologists already accept: that space is likely infinite, and that the observable universe is just a finite slice of it. If space really does go on forever, and if the laws of physics are the same everywhere, as all our evidence so far suggests, then somewhere out there, impossibly far beyond our particle horizon, but still governed by the same physics we know, there should exist regions that look almost exactly like ours. Given infinite space and a finite number of ways particles can be arranged in any given volume, statistically, some of those distant regions should even duplicate our own Milky Way, our own solar system, arranged the same way, purely by chance. It's not mysticism, it's what infinity does to probability. Level 2 is where eternal inflation lives, in Tegmark's framework. This is the collection of separate bubble universes born out of the endless inflationary process that Linda and Guth described, each one potentially operating under different physical constants, maybe even different numbers of dimensions. Because the inflating space between these bubbles keeps expanding, and expanding faster than light, they're not just far away from each other, they're causally disconnected, meaning no signal, no light, no information of any kind will ever pass between them. If level 2 bubbles exist, we are not simply unable to see them with today's telescopes. We are permanently, physically, unable to ever detect them by the very mechanism that created them. There's one more piece of this story worth knowing, because it directly answers the obvious objection anyone paying close attention should be raising by now. If separate bubble universes are permanently disconnected from ours, how could physicists ever test whether eternal inflation is real, rather than just an untestable story? A team of researchers actually tried. Starting around 2010, Stephen Feeney, Matthew Johnson, Daniel Mortlock, and Hiranya Paris, working across University College London, the Perimeter Institute, and Imperial College London, pointed out that eternal inflation carries one genuinely testable prediction. If our bubble universe ever collided with a neighboring bubble in the earliest instant of its existence, before the 2 regions were fully carried apart by inflation itself, that collision should have left a faint, specific, disc-shaped imprint on our own cosmic microwave background, a distinctive temperature pattern radiating out from a single point on the sky. The team built a dedicated computer algorithm specifically to search for that pattern, then ran it against 7 years of data from the WMAP satellite, scanning the entire sky for anything matching the predicted signature of a bubble collision. Their first published results, in 2011, found no confirmed detections. What they did produce was a rigorous upper limit, a hard statistical cap on how many detectable bubble collisions the theory could predict, while still remaining consistent with the data actually observed, essentially narrowing down how crowded the multiverse could possibly be without us having noticed by now. In a follow-up analysis using an improved algorithm, the same team flagged 4 regions of the WMAP sky where the temperature pattern looked at least broadly consistent with what a bubble collision might produce, candidates worth checking rather than confirmed detections, something the researchers themselves were careful to stress. Hiranya Paris, reflecting on the deeper motivation, called the work an opportunity to test a theory that is truly mind-blowing: the idea that we exist within a vast multiverse where other universes are colliding with our own. The team hoped that data from the more sensitive Planck satellite, once fully released, would let them refine the search further. As of the most recent published work in this specific line of research, No bubble collision signature has been confirmed, but the search itself matters enormously to the larger conversation because it's direct proof that even a multiverse theory, built on permanently disconnected regions of space, can still generate a specific, falsifiable prediction that real telescopes can go looking for, and in this case, at least partially rule out. Level 3 moves away from cosmology and into quantum mechanics, built on what's called the many worlds interpretation. This is the idea, familiar to anyone who's heard of Schrödinger's famous thought experiment with the cat in the box, that quantum events don't collapse into a single outcome the moment they're observed. Instead, every possible outcome actually happens, each one branching off into its own separate, non-communicating version of reality. In the standard telling of the cat experiment, the cat exists in a mixture of alive and dead states until the box is opened. The many worlds interpretation suggests that opening the box doesn't destroy the other possibility, it simply splits reality into two branches, one where the cat is alive, one where it isn't, with the version of you doing the observing splitting right along with it. It's worth slowing down here, because unlike the other three levels, this one didn't come out of cosmology at all, and its history is stranger and older than most people realize. The many worlds interpretation traces back to 1957, to a Princeton University doctoral thesis written by a young physicist named Hugh Everett III, under the supervision of his advisor, John Archibald Wheeler. Everett called his own approach the correlation interpretation, built around the idea of quantum entanglement, but it was Wheeler who suggested the term that stuck in the published paper, calling it the relative state formulation of quantum mechanics. Everett's core claim was radical for its time, and in some ways, it's still radical now. Standard quantum mechanics, as most physicists were taught it, said that a quantum system exists in a mixture of possible states right up until the moment it's measured or observed, at which point the wave function collapses, and one single, definite outcome gets selected, with the others simply vanishing. Everett rejected that collapse entirely. In his formulation, the wave function never collapses. Instead, every possible outcome of a quantum event actually happens, each one becoming its own separate, non-communicating branch of reality, with the version of the observer doing the measuring splitting right along with the universe itself. Reality as a whole, in Everett's picture, stays rigorously deterministic. It's only the experience of any single observer trapped inside one particular branch that looks random or uncertain. The idea landed with almost no impact at all, at first. Everett left academic physics shortly after publishing, going on to a career doing classified defense and operations research work for the Pentagon, and by most accounts, the paper sat largely ignored for over a decade. What changed its fortunes was a physicist named Bryce DeWitt at the University of Texas at Austin, who rediscovered Everett's work years later, championed it, gave it the far catchier name Many Worlds, and in the early 1970s compiled a collection of Everett's original papers alongside interpretive essays from himself, Wheeler, and others, republishing the whole body of work in a way that finally got the physics community to take it seriously. Even Wheeler's relationship with the idea was complicated. He had guided Everett's thesis and helped shape its language, yet by 1980, Wheeler had publicly disavowed the theory, reportedly uneasy with how far its implications stretched. Today, thanks largely to a separate and more modern concept called quantum decoherence, which explains mathematically why the different branches stop being able to interact with each other, Many Worlds has become one of the more seriously discussed interpretations of quantum mechanics in academic physics, even though it remains one interpretation among several competing ones, not a settled consensus. Hugh Everett's own story, away from the physics itself, ended up almost as strange as the theory he proposed, and it's worth knowing, because it explains why Many Worlds sat largely forgotten for so long. After leaving academic physics behind for a career in defense analysis, Everett became a heavy smoker and drinker, and by most accounts, a distant, largely uncommunicative father to his 2 children. He died suddenly of a heart attack in 1982, at just 51 years old, found by his teenage son at their home in Virginia. As a committed atheist who reportedly believed, half seriously, in a form of quantum immortality drawn from his own theory, Everett had asked that his remains be thrown out with the household trash rather than given any kind of funeral. His wife kept his ashes in a box for a few years, before eventually honoring the request exactly as he'd stated it. That son, Mark Everett, grew up largely estranged from his father's scientific legacy, later recalling that for most of his childhood, he thought of his dad the way he thought of the furniture, present, but essentially unknowable. Mark went on to become a musician, performing under the name E as the frontman of the band Eels, building a career, and eventually a memoir and a documentary, partly around trying to understand the brilliant, remote physicist he'd barely known. It's a strange footnote to attach to one of the more mathematically serious ideas in modern physics, that the man who first proposed a universe endlessly splitting into parallel branches spent his own life largely disconnected from the people around him, and left this world, quite literally, wanting to disappear into the ordinary and untraceable, rather than be marked by any lasting monument at all. Level 4 is where Tegmark's framework gets the most philosophical, and even researchers sympathetic to the multiverse tend to treat it with more caution. The proposal is that every self-consistent mathematical structure that could exist does exist as its own physical universe, with its own fundamental equations, not just different constants plugged into the same equations we have, but entirely different mathematics altogether. It's the most expansive version of the idea, and by most standards, the hardest to test or even meaningfully define. While Tegmark was organizing the multiverse conceptually, a separate and unrelated discovery in observational astronomy was quietly making the entire question far more urgent. In 1998, two independent teams of astronomers studying distant exploding stars called Type Ia supernovae found something nobody expected. The expansion of the universe wasn't slowing down under its own gravity, the way everyone had assumed it should be. It was speeding up, accelerating. Something was pushing space apart faster and faster over time, and whatever that something was, scientists gave it a name without fully understanding what it is: dark energy. The scale of the mystery here is almost impossible to convey properly, but the numbers give you a sense of it. The measured energy density of empty space, the vacuum, comes out to roughly 10 to the negative 29 grams per cubic centimeter. To put that in context, that figure is about 40 orders of magnitude smaller than the density of atomic nuclei, and a staggering 120 orders of magnitude smaller than what's called the Planck density, the theoretical value that quantum physics would naturally predict for the vacuum if you did the calculation the straightforward way. Physicists have never been able to explain why the actual number is so absurdly, precisely small instead of enormous, and this unsolved puzzle even has its own name in the field: the cosmological constant problem, considered one of the deepest unresolved questions in all of physics. Today, dark energy makes up roughly 68% of everything in the universe, according to data from the Planck satellite, Europe's flagship cosmology mission, which spent years mapping the cosmic microwave background in extraordinary detail. Ordinary matter, the stuff that makes up stars, planets, and everything you've ever touched, accounts for less than 5%. The rest, more than a quarter of everything, is dark matter, a separate mystery entirely, gravitationally present but invisible, and still not directly detected. Planck's 2018 data release measured the dark energy equation of state parameter at negative 1.03, remarkably close to negative 1 exactly, which is the value predicted if dark energy behaves as what Einstein originally called the cosmological constant, a fixed property of space itself rather than some evolving field. It's worth pausing on that 26.8% figure for dark matter because it's a completely different mystery from dark energy, discovered decades earlier and through a completely different line of evidence, and it deserves its own explanation before we go any further. The story starts in 1933 with a blunt, difficult Swiss astronomer named Fritz Zwicky working at Caltech, who was studying the Coma cluster, a collection of roughly 1,000 galaxies bound together by gravity. Zwicky measured how fast individual galaxies within the cluster were moving relative to each other, and the numbers didn't make sense. The galaxies were moving so quickly that the cluster's own visible mass, everything you could see and account for in stars and glowing gas, wasn't nearly enough gravity to hold it together. By Zwicky's calculation, the cluster needed to contain hundreds of times more mass than what was actually visible, or it should have flown apart long ago. Zwicky proposed that some form of unseen matter which he named dunkle materia, dark matter, must be present, providing the missing gravitational glue. Almost nobody took the idea seriously at the time. Netta Bachkol, an astrophysicist at Princeton, later described it as too outrageous to believe for almost 4 decades. That changed because of Vera Rubin, an American astronomer who, starting in the late 1960s, began systematically studying something called rotation curves, essentially, how fast stars orbit around the center of their galaxy at different distances from that center. Basic physics predicts that stars farther from a galaxy's center, out past most of its visible mass, should orbit more slowly, the same way planets farther from the Sun move more slowly than planets close in. When Rubin and her collaborator Kent Ford published their landmark 1970 study of the Andromeda Galaxy, they found the opposite. The orbital velocities of stars, far from Andromeda's center, didn't slow down at all. The rotation curve stayed almost perfectly flat, meaning stars way out at the edge of the visible galaxy were moving just as fast as stars much closer in, which should have been physically impossible unless there was a huge amount of additional invisible mass extending far beyond the visible disk, providing extra gravity to keep those outer stars from flying off into space. Rubin later recalled her own reaction to the data plainly. "I remember thinking that there must be some mechanism for speeding up stars that move too slowly, or slowing down stars that move too fast. There wasn't. What she'd found instead, confirmed across dozens of other spiral galaxies over the following years, became the most convincing evidence yet that Zwicky had been right decades earlier." Rubin herself stayed carefully agnostic about what dark matter actually was made of, whether some exotic new particle, or something more mundane like dim stars and black holes, only that there was roughly 5 to 10 times more gravitating mass out there than anything visible could account for. That mystery remains completely unsolved today. Decades of dedicated search experiments, built specifically to directly detect dark matter particles interacting with ordinary matter deep underground, shielded from cosmic rays and other interference, have come up empty so far. Dark matter is not the same thing as dark energy, even though the names sound similar, and both are, frankly, placeholder terms for things scientists don't fully understand. Dark matter pulls things together, providing extra gravity that holds galaxies and clusters intact. Dark energy pushes space apart, driving the runaway acceleration that's steadily sealing off pieces of the observable universe. Together, the two invisible components make up more than 95% of everything in existence, leaving the ordinary matter that makes up every star, planet, and person you've ever known as a genuine minority stakeholder in the universe's actual composition. Vera Rubin's own story deserves one more detail before moving on, because it says something uncomfortable about how science recognizes its own. Rubin died on December 25, 2016, at the age of 88, having spent decades as one of the most decorated astronomers alive, elected to the National Academy of Sciences, awarded the National Medal of Science in 1993, and given the Gold Medal of the Royal Astronomical Society in 1996, the first woman to receive that particular honor since Caroline Herschel, back in 1828. Every major recognition available to an astronomer eventually came her way, except the one many colleagues considered most obviously deserved. Rubin was never awarded the Nobel Prize in Physics, and because the Nobel is never given posthumously, her death permanently closed the door on it. Astronomer Emily Levesque, reflecting on the omission at the time, put it plainly: Rubin had won essentially every scientific award available to her, except the Nobel, and by that point, the gap had come to look less like an oversight than a glaring one. The frustration among physicists ran deeper than sentiment. In 2011, the Nobel Committee had honored the discovery of dark energy, work built on observations made a full 2 decades after Rubin's own rotation curve measurements, and arguably resting on evidence just as indirect as the case for dark matter itself. Rubin's own name had been floated as a leading contender for years running, with colleagues reportedly waking early each October, hoping for the call from Stockholm that never came. It's a strange footnote to leave hanging over everything this video has described about dark matter, that the observational evidence for roughly a quarter of the entire universe's total content came, in large part, from a woman whose own contribution the physics establishment never got around to formally recognizing at the highest level. in a field where, at the time of her death, exactly 2 women had ever won the physics prize in over a century of it being awarded. Here's where dark energy connects directly back to the question of what lies beyond the observable universe, and it does so in a way that's genuinely bleak if you sit with it. Because the expansion of space is accelerating, our universe is developing something called a cosmological event horizon, sometimes described using the mathematics of what's called de Sitter space. Unlike the particle horizon, which marks what we've been physically unable to see yet simply because there hasn't been enough time, the cosmological event horizon marks something permanent. Beyond a certain distance, galaxies are already receding from us faster than light can cross the expanding space in between. Any light those galaxies emit from this point forward will never, under any circumstances, reach us. Not eventually, not ever. The observable universe isn't just limited by age anymore. Thanks to dark energy, it is now actively and permanently walling itself off, and that wall will keep closing in. All of this, the accelerating expansion, the growing cosmological event horizon, the relentless dilution of dark matter and ordinary matter into an ever larger volume of space, points toward a specific long-term fate for the universe we can actually observe, one worth sitting with for a moment before we widen the lens back out to everything beyond it. If dark energy really does behave the way Planck's measurements suggest, as a constant, unchanging property of space itself, rather than something that fades or reverses over time, then the observable universe is headed toward what physicists usually call the Big Freeze, or heat death. Trillions of years from now, star formation will have used up the available hydrogen and helium gas. Existing stars will burn out one by one, and the ones that remain will fade into cooling white dwarfs, then eventually into dark, dead husks. Galaxies beyond our own local group will have already receded permanently past the cosmological event horizon long before that, invisible and unreachable. What's left, in this scenario, is an unimaginably vast, cold, dark, almost empty universe, expanding forever, approaching but never quite reaching a state of maximum entropy where nothing meaningful happens ever again. It's this same far future scenario, incidentally, that sets up the Boltzmann brain problem we'll get to shortly, since an eternal, empty, dark energy-dominated universe is exactly the kind of setting where those statistically inevitable, randomly assembled observers are predicted to eventually outnumber everyone who ever lived the ordinary way. That's the leading picture, but it isn't the only one still taken seriously. Because the exact nature of dark energy remains unknown, some researchers have explored alternative fates. If dark energy's strength were to increase without bound over time, rather than staying constant, the runaway expansion could eventually grow strong enough to tear apart galaxies, then solar systems, then planets, and finally, atoms themselves. A considerably more violent hypothetical endpoint, researchers have nicknamed the Big Rip. If dark energy instead weakened or reversed sign entirely, gravity could eventually regain the upper hand, pulling everything back together into a final collapse, sometimes called the Big Crunch, the mirror image of the Big Bang that started everything off. Current data leans heavily toward the Big Freeze as the most likely outcome, since dark energy's measured behavior lines up closely with a simple, unchanging cosmological constant, rather than something that grows or shrinks. But the honest state of the science is that the specific nature of dark energy remains one of the least understood major components of the universe, and until that changes, the universe's own long-term fate stays exactly as open a question as what lies beyond the edge of what we can currently see. That single unsettling discovery from 1998 also detonated a separate line of research in a completely different corner of theoretical physics: string theory. For years, string theory had been pursued as a hopeful path toward a single, unified theory of everything, one elegant framework underlying all the forces of nature. But the mathematics of string theory turned out to allow for an enormous number of different possible configurations, each one a self-consistent way the extra dimensions the theory requires could fold up, and each one producing its own distinct set of physical laws and constants. The commonly cited figure for how many such configurations exist is staggering: 10 to the 500th power, a number so large it dwarfs any physical quantity you could name. a number cosmologists now refer to simply as the string landscape. The connection to dark energy is direct. If the landscape really does contain something on the order of 10 to the 500th different possible vacuum states, each with its own tiny sliver of possible vacuum energy, then somewhere among that almost incomprehensible range of options, you'd expect at least some configurations to land on a vacuum energy density as small and strange as the one we actually measure, roughly 10 to the negative 120 in the units physicists use for this. It's not proof of anything, but it offered, for the first time, a mathematical reason why our universe might have such an oddly fine-tuned vacuum energy without needing to invoke some deeper, unknown principle. With enough different possible universes to choose from, an unlikely-looking outcome stops looking so unlikely. There's a third proposed resolution to that same puzzle, sitting alongside the string landscape, and it deserves mention because it comes with one of the more genuinely impressive predictions in the history of modern physics. It's called the anthropic principle, and in its most defensible form it simply says that any measurement we make of the universe is automatically filtered through the fact that we exist to make it, which rules out certain values for the fundamental constants regardless of how the underlying physics actually works. In 1987, over a decade before dark energy was even discovered, physicist Steven Weinberg, who had already won a Nobel Prize for his earlier work unifying the electromagnetic and weak nuclear forces, applied that reasoning directly to the cosmological constant problem. Weinberg calculated that if the vacuum energy of empty space were much larger than a specific very small threshold, its repulsive push would have ripped space apart so violently, so early in cosmic history, that matter would never have had the chance to clump together into stars and galaxies at all. No galaxies, in that scenario, means no planets, no biology, and no physicists around billions of years later to measure a cosmological constant in the first place. Weinberg's argument didn't tell you why the constant should be small. It told you that if you're around to ask the question, it has to be small, or you wouldn't exist to notice otherwise. Working through the numbers, Weinberg predicted a value not many orders of magnitude away from zero, a specific, falsifiable prediction published years before anyone had measured the number directly. Then, in 1998, the discovery of dark energy landed almost exactly inside the range Weinberg had calculated more than a decade earlier. It remains one of the very few times in the history of the cosmological constant problem that anyone predicted the right answer before the measurement came in, rather than explaining it afterward. Physicist Leonard Susskind, reflecting later on just how narrow that surviving range actually is, put it plainly, a cosmological constant even 10 times bigger than the value we ended up measuring would have been destructive and deadly to life, preventing stars, galaxies, and planets from ever forming. The anthropic principle and the string landscape aren't rival explanations so much as two halves of the same idea. The landscape supplies an enormous menu of possible universes, each with a different vacuum energy, and the anthropic principle explains why we'd only ever find ourselves in one of the rare entries on that menu where the number happens to be survivable. Critics of this reasoning point out that it can feel uncomfortably close to explaining away a mystery rather than solving it, since it doesn't predict a single specific value, only a range compatible with the observer doing the calculating. Weinberg himself, largely, stayed out of the philosophical arguments that followed, content, by most accounts, with having used the reasoning to make one correct, testable prediction about the actual universe we live in. There's another idea from theoretical physics worth pulling into this picture, one that approaches the question of what's beyond us from a completely different angle, not by asking how big space is, but by asking how much information a region of space can actually hold. It's called the holographic principle, and it grew out of black hole physics in the 1970s. Physicist Jacob Bekenstein found that the maximum entropy, essentially the maximum amount of information that can be packed into a black hole, isn't determined by its volume, the way you'd naturally expect, but by the surface area of its event horizon instead. That result seems strange enough on its own, but in 1993, physicist Gerard Hooft proposed generalizing it into a full principle, that the maximum amount of information contained in any region of space, not just inside black holes, is limited by the area of the boundary surrounding that region, not by how much three-dimensional space is inside it. In 1995, Leonard Susskind developed the idea further and gave it real mathematical teeth, arguing that everything happening inside a volume of space could, in principle, be fully described by information encoded on its outer boundary, the same way a two-dimensional hologram can encode a full three-dimensional image. In 1997, physicist Juan Maldacena provided what many theoretical physicists consider the strongest evidence yet for the idea, a mathematical duality, now called the ADS or CFT correspondence, showing that a theory of gravity operating inside a certain kind of curved space is mathematically identical to a completely different theory, without gravity, living on that space's boundary. If the holographic principle applies to the universe as a whole, and that remains a genuinely open question, it would mean everything you experience as three-dimensional depth and volume might, at some deeper mathematical level, be a projection of information stored on a much simpler surface, a possibility that sounds more like a plot device from a movie than serious physics. And yet, it's been taken seriously by some of the most respected researchers in the field for 3 decades now. There's one more kind of bubble worth mentioning before we move on, and unlike the pocket universes born from eternal inflation, this one wouldn't be off in some permanently unreachable corner of the multiverse. It could, in principle, start right here. The idea is called vacuum decay, and it grows out of a genuinely uncomfortable discovery made at the Large Hadron Collider in 2012, when physicists finally pinned down the mass of the Higgs boson, the particle responsible for giving other particles their mass, at right around 125 billion electron volts. That specific number, combined with the separately measured mass of the top quark, places the physics of our universe in an unsettling zone. Running the equations of the Standard Model forward, using the Higgs field's own properties, suggests that the vacuum we're living in, the actual, ordinary emptiness of space, may not be the lowest possible energy state available to it. It might instead be what physicists call a false vacuum, sitting in a shallow dip rather than the deepest possible valley, the way a marble can rest in a small pocket partway down a hillside, without having rolled all the way to the bottom. If that's correct, then somewhere, at some unpredictable point, an extraordinarily rare quantum fluctuation could nucleate a tiny bubble of genuine, lower energy, true vacuum, and physicists Michael Turner and Frank Wilczek worked out the terrifying mechanics of what would happen next in a 1982 paper published in Nature. That bubble wouldn't stay small. It would expand outward in every direction at very close to the speed of light, rewriting the fundamental laws of physics as it went, converting everything it swept through, atoms, stars, galaxies, into whatever new, lower energy configuration the true vacuum represents. Because the bubble's edge would move at essentially light speed, there would be no possible warning. Nothing could outrun it, and nothing on the wrong side of that expanding wall would ever see it coming. Before this sounds like an imminent threat worth losing sleep over, it's worth being precise about what the physics actually says. The fact that our universe has already existed for 13.8 billion years without this happening is itself a powerful piece of evidence that if our vacuum truly is metastable, its lifetime is enormously longer than the current age of the universe, likely by many, many orders of magnitude. Whether the Standard Model, extrapolated all the way up to the highest energies physics can describe, truly does predict this kind of instability, or whether some undiscovered physics beyond the Standard Model stabilizes the vacuum entirely, remains genuinely unresolved, and settling it may require measuring the Higgs boson's own self-interaction with a precision beyond what even the Large Hadron Collider can currently achieve. It's an odd thought to end on, that the same basic physics responsible for bubble universes branching off into an eternally inflating multiverse also describes, in a completely different context, a bubble that could just as easily start on the inside, converting our own observable universe into something else entirely, with absolutely no warning at all. None of this settles the actual shape of space itself, and that question, whether the universe is flat, curved like the inside of a saddle, or curved like the surface of a sphere, matters enormously for what beyond the observable universe could even mean. The Planck satellite's 2018 full mission data, combining its measurements of the cosmic microwave background with information about how that background light gets bent by gravitational lensing, along with independent data from baryon acoustic oscillations, found the universe to be flat to within about 0.4%, an astonishingly precise result. A flat universe, in the geometry cosmologists use, is fully consistent with space being infinite in extent, stretching forever in every direction without ever curving back on itself. But the story isn't perfectly settled, and this is worth being honest about. A separate reanalysis, using only Planck's temperature and polarization data, without folding in the lensing measurements, found a value suggesting the universe might actually be very slightly closed, curved, like the surface of an enormous sphere, a result significant enough that some researchers publicly called it a potential crisis for cosmology. If that finding held up, it would mean the universe, while still almost inconceivably vast, could technically be finite, unbounded, the way the surface of a sphere has no edge you can walk off of, but still not infinite. When the full dataset, lensing included, gets folded back in, the preference shifts back toward flatness, and most researchers in the field, including the Planck collaboration itself, suspect the curvature signal may be the result of an unaccounted-for systematic error in the data rather than a real detection. The debate hasn't fully closed, but flatness remains the leading, best-supported picture. Here's a distinction that even a lot of cosmology enthusiasts miss, though. Flatness and infinity aren't actually the same question. A universe can be geometrically flat, meaning parallel lines never converge or diverge, and still be finite, if its overall shape loops back on itself in a way that has nothing to do with curvature, a property mathematicians call topology rather than geometry. Picture the old video game trick, where a spaceship flies off the right edge of the screen and reappears on the left. That's a flat space with a looped topology, and cosmologists have seriously investigated whether our own universe might work the same way. In 2003, French astrophysicist Jean-Pierre Luminet and his collaborators proposed a specific version of this idea, suggesting the universe might have the topology of a Poincaré dodecahedral space, a finite, 12-sided shape that connects back on itself. Put forward as a possible explanation for a mild anomaly WMAP had detected in the largest scale patterns of the cosmic microwave background. It was a genuinely serious proposal, published and debated in the scientific literature. It just hasn't held up. Later, more precise data from Planck found no compelling evidence for that dodecahedral topology, or for any other detectable looped topology. And the simplest picture, an ordinary flat, likely infinite universe with no looping, remains the model that best fits everything we've measured. The idea is a useful reminder, though, that even flat can hide surprises, and that cosmologists have genuinely tested and mostly ruled out some of the stranger possibilities for the universe's overall shape. There's one genuinely unresolved anomaly buried inside the cosmic microwave background that deserves mention on its own, because if it holds up, it would strike directly at one of the most basic assumptions underpinning everything else in this video. Cosmologists build their models on something called the cosmological principle, the working assumption that the universe has no special direction and no privileged location, that on the largest scales, it looks roughly the same no matter which way you point a telescope. In 2005, physicists Kate Land and João Magejo, examining early data from the WMAP satellite, found something that shouldn't exist if that principle holds exactly true. The two largest scale temperature patterns in the cosmic microwave background, called the quadrupole and the octopole, appeared to be unusually aligned with each other, both oriented along a shared axis in the sky, rather than pointing in random, unrelated directions the way statistical isotropy would predict. Land and Magejo, borrowing a piece of contemporary political rhetoric for the name, dubbed the anomaly the axis of evil, and follow-up analysis found the alignment extended to include several additional, smaller-scale patterns as well, with the odds of this particular arrangement happening purely by chance, estimated at less than 0.3%. What makes the anomaly stranger still, and considerably harder to dismiss as pure coincidence, is where that shared axis actually points. It lines up disturbingly closely with the plane of our own solar system, the ecliptic, the same flat plane the planets orbit within. If real, that would suggest the oldest light in the universe somehow knows where our own solar system happens to sit, a direct, unsettling challenge to the Copernican principle, the broader assumption running through essentially all of modern astronomy that Earth doesn't occupy any special or privileged position in the cosmos. The anomaly has persisted across multiple independent datasets, including the European Space Agency's Planck satellite, which measured the cosmic microwave background at roughly 10 times WMAP sensitivity and still found the same alignment sitting in the data. That persistence across two entirely separate satellites, built by different space agencies using different instruments, has made the anomaly considerably harder to wave away as a simple measurement error or an artifact of removing the bright band of foreground light from our own galaxy out of the map. Even so, the significance of the axis of evil remains genuinely disputed within cosmology, rather than broadly accepted as a real feature of the universe. Researchers examining the effect closely have pointed out that the exact statistical alignment shifts noticeably depending on precisely how you process and clean the raw satellite data, which is exactly the kind of instability you'd expect from a subtle, difficult to fully remove systematic effect, rather than genuine, new physics. Most cosmologists currently treat the anomaly as an open, low-priority puzzle rather than grounds for abandoning the cosmological principle. But it's never been fully explained away either. It sits there, quietly, at the very largest scales of the oldest light in the universe, an unresolved and still faintly possible crack in the assumption that nothing about our own particular corner of space is special, buried inside the same dataset that gave us almost everything else described in this video. And here's a detail that undercuts any confidence anyone might have that this subject is fully settled science with no loose threads left. Cosmologists cannot currently agree on precisely how fast the universe is expanding right now, today. And the disagreement isn't a small rounding error. It's called the Hubble tension, and it comes down to two different, independently rigorous ways of measuring the same number. The Hubble constant, which describes how many kilometers per second faster a galaxy appears to recede for every additional megaparsec of distance from us. Measure it using the cosmic microwave background, the way Planck's satellite data does, feeding those early universe conditions into the standard cosmological model, and you get a value of about 67.4 kilometers per second per megaparsec. Measure it a completely different way, using what's called the cosmic distance ladder, calibrating the brightness of pulsating stars called Cepheid variables and exploding stars called Type Ia supernovae in nearby galaxies, the method championed by the SH0ES collaboration, and you get a noticeably higher value, around 73 kilometers per second per megaparsec. That's roughly a 9% gap between two methods that are each individually extremely precise, and by the early 2020s, the discrepancy had grown statistically significant enough, past what's called 5 sigma confidence, that random chance became a vanishingly unlikely explanation. Many researchers hoped the James Webb Space Telescope, with its sharper resolution, would resolve the disagreement once it came online, by ruling out the possibility that the local Cepheid measurements were being thrown off by interstellar dust or overcrowded star fields. It didn't resolve anything. Observations using JAST in 2024 and 2025 confirmed that the original Hubble Space Telescope measurements had been accurate all along, which, rather than settling the dispute, deepened it, since the leading explanation for an error had just been ruled out. As of early 2026, cosmologists still don't have a single agreed number for how fast the universe around us is expanding, and prominent researchers in the field, including Daniel Skolnick, one of the physicists most closely associated with the local distance ladder measurements, have started describing the situation in stronger language than tension, calling it an outright crisis for the standard model of cosmology. Nobody knows yet whether the resolution will turn out to be some unaccounted-for measurement error or a genuine crack in the physics underlying the entire picture we've been building throughout this video. Either way, it's a useful reminder that even the most basic number in cosmology, how fast the universe you're sitting inside of is currently stretching, is still an open, actively contested question. Everything this video has described so far about dark energy treats it as a fixed, unchanging property of space, a simple cosmological constant, because that's what the evidence pointed toward for most of the last 2 decades. that picture may already be cracking. Starting in 2024, the Dark Energy Spectroscopic Instrument, DESI, a survey mounted on a telescope at Kitt Peak National Observatory in Arizona, capable of measuring the light from thousands of galaxies and quasars simultaneously, began releasing results from the largest three-dimensional map of the universe ever constructed, based on precise distance measurements to millions of galaxies stretching back across most of cosmic history. The first year of data, released in April of 2024, already showed a mild but noticeable preference for dark energy that changes over time, rather than staying constant the way Einstein's cosmological constant would require. Researchers were cautious. A single, unexpected signal in one dataset is exactly the kind of thing that tends to evaporate once more data comes in. It didn't evaporate. When DESI released its second year of data in 2025, drawing on roughly 14 million precise galaxy and quasar redshift measurements, more than double the sample size of the first release, the hint toward evolving dark energy grew stronger rather than weaker. Combined with independent data from distant supernovae and the cosmic microwave background, several separate research teams found evidence for time-varying dark energy at a statistical significance ranging from roughly 2.5 to nearly 4 sigma, depending on exactly which supernova dataset was folded into the analysis, edging closer to, though still short of, the 5 sigma threshold physicists typically require before calling something a confirmed discovery. The specific pattern researchers found is genuinely strange. The data suggest dark energy may have been slightly stronger, in a technical sense called phantom-like, in the earlier universe, and has been gradually weakening since, a behavior no simple version of the cosmological constant can produce, since a true constant, definitionally, doesn't change at all. One member of the DESI collaboration summarized the situation for the public plainly, saying it's looking more and more like the standard model of cosmology may need to be modified to make the different datasets agree, and that evolving dark energy currently looks like the most promising direction. It's not a settled result. Several independent groups of researchers have pushed back, arguing that specific systematic effects, particularly involving how certain distant supernovae are calibrated and how dust in our own galaxy is corrected for, could be producing an artificial signal that mimics evolving dark energy without any new physics actually being required. The debate is active and ongoing as of this recording. But if the evolving dark energy signal holds up under further scrutiny, from DESI's continuing data releases, and from a new generation of instruments specifically built to test it, it would mean scientists have been quietly mismodeling one of the 3 or 4 largest components of the entire universe for the past 2 decades, and it would reopen, from a completely different angle, the very question this whole video has been circling. Whatever dark energy actually is, and whatever mechanism is driving it, that mechanism reaches out past the observable universe as certainly as anything else discussed here, since it's the same underlying physics, whatever it turns out to be, that determined how our observable patch of space came to look the way it does. If dark energy really is evolving over cosmic time, the way DESI's data increasingly suggests, physicists need some actual physical mechanism to explain how, since a true cosmological constant, by definition, cannot change. The leading theoretical candidate is called quintessence, a name borrowed from the ancient concept of a 5th fundamental element beyond earth, air, fire, and water. In quintessence models, dark energy isn't a fixed property of empty space at all, but a genuine, dynamic field permeating the universe, similar in spirit to the inflaton field thought to have driven inflation itself in the universe's first fraction of a second, except operating today on cosmological timescales rather than in a single, brief early burst. Because a field like this can change its value and its energy density over time as the universe expands, it can naturally produce exactly the kind of gradually weakening, time-varying dark energy that DESI's baryon acoustic oscillation data has been hinting at, something a simple, unchanging cosmological constant is mathematically incapable of doing. Physicists studying the DESI results have already begun working out what a successful quintessence model would need to look like to fit the data, and the early attempts, published through 2024 and 2025, have found that reasonably simple versions of the theory can reproduce the observed pattern, even accounting for the specific, somewhat unusual behavior the data suggests, that dark energy may have briefly dipped into what's called a phantom-like state, a technical regime where its effective pressure becomes even more negative than a standard cosmological constant would allow, before settling back toward more ordinary quintessence-like behavior more recently in cosmic history. None of this is settled physics. Quintessence remains one of several competing theoretical frameworks being tested against the incoming data, alongside other proposals in which dark energy interacts weakly with dark matter itself, gradually exchanging energy between the two, and alongside the more conservative possibility that the entire evolving signal traces back to nothing more exotic than an unaccounted-for calibration error in how certain supernovae are measured. What's genuinely new, though, is that for the first time in over 2 decades, dark energy has stopped being treated as a single, silent, unchanging number sitting quietly in Einstein's equations, and has become, once again, an active, unresolved area of theoretical and observational research, with real data now capable of distinguishing between competing physical models rather than simply confirming the same constant value survey after survey. There's one more measuring technique worth understanding, because it's the specific tool responsible for DESI's evolving dark energy hints, and it works on a completely different principle than either parallax or standard candles. It's called baryon acoustic oscillation, and its origin traces back to the same hot, dense early universe responsible for the cosmic microwave background itself. Before the universe cooled enough for atoms to form, ordinary matter and light were still tightly coupled together, and tiny density fluctuations in that early plasma sent literal sound waves rippling outward through it, compressions and rarefactions traveling at a significant fraction of the speed of light. When the universe cooled enough, at the same 380,000-year mark that released the cosmic microwave background, those pressure waves suddenly froze in place, stopped in their tracks, leaving behind a very faint, very specific preferred distance between regions of slightly higher matter density, baked permanently into the large-scale structure of the universe. That frozen distance, calculated precisely from cosmic microwave background physics, works out to a bit under 500 million light-years in today's expanded universe, and it functions as what cosmologists call a standard ruler, the geometric equivalent of a standard candle. Just as a standard candle's known true brightness lets you calculate distance from how dim it appears, a standard ruler's known true length lets you calculate distance from how large it appears on the sky. Galaxies across the universe show a very slight statistical tendency to cluster at multiples of that same frozen distance, an echo of the ancient sound waves rippling through the early universe. And by measuring how large that characteristic clustering distance appears at different points across cosmic history, instruments like DESI can map out exactly how the universe's expansion rate has changed over billions of years, entirely independent of supernovae or Cepheid variables. It's this baryon acoustic oscillation technique, applied across 14 million galaxies and quasars, that produced the specific evolving dark energy signal described earlier in this video, a completely different measuring method than the distance ladder built on Leavitt's original insight, yet one that traces back to the exact same 380,000-year-old moment in cosmic history as the cosmic microwave background itself, the frozen echo of sound waves from the universe's own infancy still being read off the sky today. There's a strange, easily overlooked detail buried inside that same cosmic microwave background data, one that reveals something surprising about our own motion through space, and it's worth a detour before moving on. When researchers first mapped the cosmic microwave background in fine detail, back in the 1970s, they noticed the sky wasn't perfectly uniform after all, not because the early universe itself was lopsided, but because of something far closer to home. Our own galaxy is moving. The microwave background appears very slightly warmer on one side of the sky and very slightly cooler on the opposite side, a pattern called the CMB dipole, caused by the ordinary Doppler effect, the same physics that makes an ambulance siren sound higher pitched as it approaches and lower as it recedes. Measurements using data from the COBE satellite pinned the effect down precisely, showing that the local group of galaxies, our own Milky Way included, is moving relative to the cosmic microwave background's own rest frame at a speed of roughly 627 kilometers per second, in a specific, well-established direction on the sky. That's an enormous speed for something as massive as an entire cluster of galaxies, over 2 million kilometers per hour, and for a while, nobody knew exactly what was pulling us. Astronomers eventually traced the motion to a concentration of mass roughly 220 million light-years away, hidden almost directly behind the dense band of our own galaxy's disk, a region so obscured by the Milky Way's own stars and dust that astronomers still refer to it as the zone of avoidance. They named the unseen mass responsible the Great Attractor. In 2014, a team of astronomers led by R. Brent Tully mapped out the larger structure the Great Attractor sits inside, an enormous supercluster of roughly 100,000 galaxies, spanning more than 500 million light-years, which they named Laniakea, Hawaiian for immense heaven, a fitting name for the structure that turns out to contain our own Milky Way as a comparatively tiny member. Even Laniakea itself isn't the final word. Some of that same large-scale motion appears to continue converging toward an even more distant, even more massive concentration of galaxies called the Shapley supercluster, hundreds of millions of light-years further out, suggesting the gravitational structure pulling our galaxy through space nests inside still larger structures beyond it. It's a useful, grounding reminder buried inside an otherwise dizzying subject. Long before you get anywhere near speculative bubble universes or branching quantum realities, the ordinary, well-measured universe already has us hurtling through space at over 2 million kilometers an hour, pulled by the combined gravity of structures so large that mapping just the nearest layer of them took until 2014, tucked partly out of view behind our own galaxy's disk this entire time. It's worth pausing here to say plainly what all of this does and doesn't prove, because it's easy for the multiverse and eternal inflation to sound like established fact rather than what they actually are. The best current extrapolation from a theory, inflation, that itself has strong, though not universal, observational support. Inflation was originally proposed to solve specific, well-defined problems with the horizon and the flatness of space. And in the decades since, its broader predictions, like the specific statistical pattern of tiny temperature fluctuations in the cosmic microwave background, have held up extremely well against precision measurements. But the leap from inflation happening once in our universe to inflation happening eternally in an endless number of separate bubble universes we can never observe is a much bigger and much harder claim to test. That's the core criticism serious physicists raise, and it's not a fringe objection. If separate bubble universes are, by their very nature, permanently disconnected from anything we could ever measure or detect, in what sense is their existence a scientific claim rather than a philosophical one? Critics have argued this cuts against a basic requirement most scientific theories are expected to meet: the ability, at least in principle, to be tested and potentially proven wrong. Guth and Linde, and most of the physicists who've worked on eternal inflation since, have continued to defend the theory's scientific standing, arguing that even though individual bubble universes can't be directly observed, the underlying theory of inflation that predicts them can still be tested through its other observable consequences here in our own universe. The debate over whether that's a satisfying answer continues. There's a second, related puzzle that comes up constantly in discussions of eternal inflation, one that even its strongest defenders admit remains genuinely unsolved. If inflation really does produce infinitely many bubble universes, stretching forward in time forever, how do you even define what's typical, or likely, or probable among an infinite set? Physicists call this the measure problem, and it's proven remarkably resistant to a clean solution. Alan Guth once illustrated the strangeness of the issue with a memorably odd example, pointing out that in an infinite multiverse with infinite possible variations, you'd expect there to be more universes containing bizarre statistical flukes, like two-headed cows, than universes like our own that happen to look ordinary and expected, simply because there are more ways to be unusual than to be typical. Nobody has fully resolved how to make sense of probability itself once you're dealing with true infinities of separate universes, and that unresolved mathematical problem sits underneath almost every serious multiverse claim being made today. The measure problem gets even stranger once you follow it to its most uncomfortable conclusion, one that cosmologists take seriously enough to have given it its own name: the Boltzmann brain problem. If eternal inflation is correct, and if the far future of our own universe really does settle into an eternal, nearly empty state dominated by dark energy, the way current data suggests it will, then that empty state still has a temperature and a finite entropy tied to its cosmological horizon, and it lasts for an infinite stretch of time. Given infinite time, even wildly improbable events become effectively guaranteed to happen eventually, over and over, an infinite number of times. And one of the events that becomes guaranteed, statistically, is that random thermal and quantum fluctuations in that empty space could occasionally assemble a self-aware, conscious brain, complete with false memories of an entire lifetime that never actually happened, flickering into existence for a moment before dissolving back into the vacuum. Physicists Andreas Albrecht and Lorenzo Sorbo formalized this scenario in a 2004 paper and gave these hypothetical observers their name, Boltzmann brains, after the 19th century physicist Ludwig Boltzmann, whose work on statistical mechanics first raised similar questions about improbable fluctuations. The unsettling part is the math. In most versions of eternal inflation, it takes vastly less entropy and is therefore vastly more statistically likely for random fluctuations to spontaneously assemble a single isolated brain than it is for them to produce an entire orderly galaxy full of ordinary observers who evolved the normal way, through billions of years of stars and planets and biology. Run the numbers out to infinity, and in many models, Boltzmann brains should vastly, almost incomprehensibly, outnumber ordinary observers like us across the multiverse as a whole. Alan Guth, Andrei Linde, and Alexander Vilenkin, three of the very physicists who built eternal inflation in the first place, later co-authored a 2010 paper directly confronting this problem, exploring which mathematical choices about how to measure infinities might avoid the conclusion that observers like us should be a vanishing statistical minority compared to randomly assembled brains. It remains, by the admission of researchers working on it, one of the strangest unresolved puzzles tied to the multiverse, a place where the theory's own infinite scale seems to threaten to undermine the reliability of the very observations used to support it in the first place. Not every physicist who thinks seriously about what came before, or lies beyond, the observable universe accepts the inflation and multiverse picture at all. The most prominent alternative comes from Roger Penrose, the British mathematical physicist who shared the 2020 Nobel Prize in Physics for earlier, unrelated work, proving that black holes are a robust prediction of general relativity. Starting with a 2010 book called Cycles of Time, Penrose laid out a framework he calls conformal cyclic cosmology, or CCC, which rejects the idea of a single Big Bang entirely, in favor of an endless sequence of cosmic cycles Penrose calls aeons. In Penrose's model, our current universe is only one aeon in an infinite chain of them. Each aeon begins with what looks, from the inside, like a Big Bang, and ends, unimaginably far in the future, in a state of maximum expansion, so cold, so dark, and so empty that it's dominated entirely by massless particles, like photons and gravitons, drifting through nearly empty space. Penrose's key mathematical insight is that in a universe containing only massless particles, the normal notion of distance and timescale stops mattering in a specific technical sense called conformal geometry, which allows that maximally expanded, dying end state of one aeon to be mathematically stitched directly onto the fiery beginning of the next, without needing a singularity or a moment of true nothingness in between. Working with Armenian physicist Vahe Gurzadyan, Penrose went looking for direct observational evidence of this idea inside the cosmic microwave background itself, reasoning that violent events from the aeon before ours, specifically collisions and mergers between enormous supermassive black holes, might leave faint imprints on the CMB of our own aeon, showing up as families of concentric circles where the temperature varies unusually little. In 2010, Gurzadyan and Penrose published a paper claiming to have found exactly that in WMAP data, reporting the detection at a statistical significance of 6 sigma, an extremely high bar in physics, and suggesting they'd also found what they called Hawking points, bright spots that would mark the final evaporation of individual black holes from the previous eon. The claim generated immediate, sustained skepticism. At least 3 independent research groups attempted to reproduce the result using standard simulations of the CMB based on the accepted lambda-CDM model of cosmology, and all 3 found that the supposed concentric circles were statistically indistinguishable from what you'd expect in ordinary random noise, no different from patterns that show up by chance in any large dataset if you go looking hard enough. A more recent, high-resolution 2024 reanalysis using a machine learning system built specifically to search for these patterns traced the apparent detections back to a small number of unusually bright or dark pixels in the data, and found that once those outlier pixels were properly accounted for, no statistically significant circles remained at all. Penrose and Ghazardian have continued to defend their analysis and have published further papers pushing back on the critiques, keeping the debate technically open, but conformal cyclic cosmology remains, by any reasonable account, a minority position, an elegant and mathematically serious alternative to inflation, but one that has not found the kind of independent observational support that would move it into the scientific mainstream. Every single fact in this video points toward a universe that is staggeringly, almost incomprehensibly large, and possibly infinite. That scale runs headlong into one of the oldest, most stubborn puzzles in modern science, one that connects directly back to everything we've covered. In the summer of 1950, physicist Enrico Fermi, one of the key figures behind the first controlled nuclear reaction and a central member of the Manhattan Project, was walking to lunch with colleagues at the Los Alamos National Laboratory in New Mexico. The conversation had turned, casually, to flying saucers and the wave of UFO reports popular at the time. Partway through, according to several colleagues who were present, Fermi asked a question that's remained essentially unanswered for over 70 years. Where is everybody? His reasoning, worked out largely in his head in the span of a lunchtime conversation, a skill he was famous for throughout his career, was straightforward. Given the sheer number of stars in our galaxy alone, the amount of time the galaxy has existed, and even a conservative estimate for how fast a civilization could spread using ordinary technology, any advanced civilization that arose practically anywhere in the Milky Way should have had more than enough time to colonize, or at least make its presence detectable across the entire galaxy by now. And yet, looking up at the sky, we see nothing. No signals, no probes, no evidence of any kind. In 1961, astronomer Frank Drake tried to put some actual numbers behind the question, formulating what's now called the Drake equation, a chain of multiplied probabilities meant to estimate how many active, communicating civilizations might currently exist in the Milky Way. It multiplies things like the rate of star formation, the fraction of stars with planets, the fraction of those planets capable of supporting life, the fraction where life actually develops, the fraction where that life becomes intelligent and communicative, and finally, how long such a civilization tends to survive before it goes silent, whether through collapse, self-destruction, or something else entirely. Several of those variables were essentially unknown guesses in 1961. Decades of exoplanet research have since pinned some of them down considerably, confirming that planets, including many roughly Earth-sized and orbiting in a habitable zone, appear to be common around other stars. Other variables in the equation, especially the fraction of habitable planets where intelligent, communicative life actually emerges and how long such civilizations typically last, remain almost entirely unconstrained. None of this is really a niche curiosity tacked onto the end of a cosmology video. It's arguably the single most direct, human-scale consequence of everything we've covered about the universe's size. If the observable universe alone contains a minimum of 2 trillion galaxies, and if inflation really does mean uncountably more space, and possibly infinitely many separate pocket universes exist beyond what we can see, then the raw numbers involved in the Drake equation become almost impossible to interpret in any way other than life, somewhere, at some point, seeming statistically close to inevitable. And yet, as far as our instruments have ever been able to tell, in over 70 years of increasingly sophisticated searching, the sky has stayed completely silent. Proposed resolutions range from the mundane, that intelligent life might simply be exceptionally rare, or that civilizations reliably destroy themselves before they're capable of interstellar communication, to the genuinely unsettling that advanced civilizations exist but have specific reasons to stay hidden. No explanation has been confirmed. The silence, as researchers in the field often put it, remains the central mystery, and it's one that gets stranger, not less strange, the more we learn about just how much universe is actually out there for that silence to be filling. So where does that leave the honest answer to the question this video opened with? What exists beyond the observable universe? The most defensible, most widely supported answer among working cosmologists is also the least dramatic-sounding one: almost certainly more universe. More space, more galaxies, governed by the same laws of physics we already know, simply too far away for their light to have ever reached us, and in many cases permanently sealed off from ever reaching us at all, because of the accelerating expansion driven by dark energy. That alone is already a staggering claim, one grounded in solid, repeatedly tested physics. General relativity, the measured flatness of space, and the observed uniformity of the cosmic microwave background all point toward a universe that continues, essentially unchanged in its basic physics, far beyond what any telescope will ever capture. Beyond that baseline picture, the answer gets progressively more speculative and progressively stranger, layer by layer. If eternal inflation is correct, and a meaningful fraction of working cosmologists think it likely is, given how well the underlying inflation theory has performed, then beyond our observable universe sits not just more of the same kind of space, but an unknown, possibly infinite number of separate pocket universes, born out of an inflating background that never stopped repeating the process that created our own universe roughly 13.8 billion years ago. Some of those universes, if the string landscape framework holds any truth, could operate under entirely different physical constants, different vacuum energies, quite possibly different numbers of dimensions, each one a self-consistent but wildly different version of reality, permanently and physically unreachable from our own. And underneath even that, running in parallel rather than sitting somewhere distant in space, sits the possibility raised by quantum mechanics itself, that every measurement, every decision point at the quantum level, has been splitting reality into branching, non-communicating versions since the beginning of time, meaning the multiverse might not even require distance to exist. It might already be here, layered invisibly against the version of events you're currently experiencing. And running alongside all of it sits Penrose's very different proposal, that there's no need for parallel space at all, that what lies beyond isn't sideways, into other bubbles or other branches, but forward and backward in time, into an endless chain of aeons that came before ours and will come after, each one a full universe, born, aging, dying, and giving birth to the next. None of these ideas require abandoning science for speculation. Every piece of this picture traces back to a specific, published, peer-reviewed line of research: Penzias and Wilson's 1965 discovery of the cosmic microwave background, the COBE, WMAP, and Planck missions that mapped it in ever greater detail, Guth's 1981 paper Solving the Horizon, flatness and monopole problems, Linday's 1982 breakthrough on the graceful exit problem and his subsequent recognition that inflation could run forever, Everett's 1957 quantum mechanics thesis and its decades-later revival by DeWitt, the 1998 supernova surveys that revealed dark energy and rewrote our understanding of the universe's fate, the theoretical work on the holographic principle from Bekenstein, Hooft, Susskind, and Maldacena, the precision measurements from the Planck satellite that have pinned down the geometry of space to within a fraction of a percent, and Penrose and Gurzadian's contested but genuinely tested search for evidence of a universe before our own. What's speculative isn't the physics. What's speculative is how far you're willing to extrapolate that physics past the point where we can ever directly check it. Take a step back and look at everything that's actually gone into answering this video's opening question, and the honest shape of it is worth sitting with. This wasn't a story with one clean discovery and one clean answer. It was a slow, difficult, multi-generational accumulation of evidence, starting with two radio astronomers who thought pigeon droppings were interfering with their antenna, running through a Belgian priest whose mathematics Einstein initially called abominable, a rival theory named mockingly on live radio that ended up giving the real theory its permanent name, a woman blinking between photographic plates by hand to invent the entire concept of a standard candle, and a young graduate student whose thesis was ignored for over a decade before it became one of the most seriously debated ideas in physics. None of it arrived neatly. Almost every major piece of this picture, the microwave background, the accelerating expansion, the flatness of space, the mass of dark matter, was found by people looking for something else entirely, or by people whose results were initially doubted, dismissed, or in Bicep 2's case, walked back publicly within a year of an international announcement. That messiness is exactly what makes the current picture trustworthy rather than despite it. Science that arrives at the same answer through completely independent, unrelated paths, the microwave background's uniform temperature, the primordial abundance of helium, the measured flatness of space, the statistical pattern of the CMB's temperature ripples, tends to be considerably more reliable than any single, isolated result, however dramatic. And by that standard, the core claim underlying everything in this video, that the observable universe is a tiny, arbitrarily bounded fraction of something enormously larger, rests on about as solid a foundation as cosmology currently has to offer. Even while huge specific pieces of the picture, what dark energy actually is, whether it changes over time, why the vacuum has the exact energy density it does, whether eternal inflation can even be tested in principle, remain wide open. What we know for certain is this: 13.8 billion years ago, something happened that we still don't fully understand, and in an unimaginably brief instant afterward, space itself stretched by a factor large enough to smooth out the universe we now observe. 93 billion light-years of that stretched space is currently visible to us, filled with roughly the same billions of galaxies astronomers have spent the last century cataloguing, first glimpsed as a mysterious hiss of radio noise in a New Jersey antenna, then mapped in ever finer detail by 3 generations of orbiting satellites. And every single day, dark energy pulls a little more of that observable slice permanently out of reach, sealing off pieces of the cosmos we will never see again, while the underlying theory that best explains how any of this got started predicts, almost as a side effect, that what we're looking at was never the whole story to begin with. Somewhere out past 46.5 billion light-years, in every direction at once, the universe simply keeps going, and the honest, current, best answer to what's out there is that nobody alive today will ever know for certain, only that the physics says it's almost certainly still there. It's worth closing out the numbers portion of this video with the single largest, roundest figure the whole subject produces, if only because it's the number most likely to actually stick with you after everything else fades. Multiply the 2 trillion galaxies inside the observable universe by a rough estimate of 100 billion stars per galaxy, itself an average drawn from studying galaxies of wildly different sizes, and you land on a number in the neighborhood of 1 septillion, a 1 followed by 24 zeros. Different methods and different assumptions about how many small, faint galaxies and dim, hard-to-detect stars actually exist push published estimates anywhere from around 10 sextillion on the low end up towards several septillion on the high end. But even the most conservative, careful estimates land solidly in a range that stopped being meaningfully comprehensible to the human brain a long time ago. Astronomers commonly reach for the same comparison to try to make the figure land. There are more stars in the observable universe than there are individual grains of sand on every beach and in every desert on Earth combined, by a factor most estimates put somewhere around 20 or 30 to 1. And every single one of those stars, across 2 trillion galaxies, sits inside the 93 billion light-year sphere this entire video has been describing as a comparatively tiny fraction of everything that actually exists. It's the number that makes the video's opening question feel less like idle speculation and more like an almost unavoidable one. A universe finite enough to fully catalogue might reasonably be expected to be finite in every other sense too, small enough that its physics, its origin, and its boundaries could eventually all be pinned down completely. A universe holding a septillion stars inside a boundary that current physics treats as arbitrary rather than absolute, a boundary set only by the age of the universe and the finite speed of light, is a very different kind of place, And it's exactly the kind of place where the honest, current, best scientific answer to what lies beyond it remains, as this whole video has tried to show, almost certainly more. Zoom in past the stars themselves, down to the level of individual atoms, and the numbers get stranger rather than more manageable. Physicists commonly cite a figure of around 10 to the 80th power protons in the observable universe, a number derived from the same basic measurements of average matter density that Planck and its predecessor missions pinned down through the cosmic microwave background, combined with the total volume of the observable universe itself. 10 to the 80th is already so large that comparing it to anything in ordinary experience stops being useful. It dwarfs the number of grains of sand, the number of stars, even the number of seconds that have passed since the Big Bang, by margins that are themselves almost impossible to state meaningfully. And that number, staggering as it is, still only describes the ordinary, baryonic matter making up less than 5% of the universe's total content, a fraction of the census this video has already walked through in detail, dark matter, dark energy, and all. If this kind of deep dive into cosmology is something you want more of, make sure you're subscribed, because there's a lot more of the universe left to cover.